This is the completion of our notes from today. We left off with number 7 in alternating series. We know that it's alternating series because we see this term here, -1 to the n, which means when we're at an odd power, we'll have subtraction, addition, subtraction, addition for each even and odd value for n. So we know it's an alternating series. Since it's an alternating series, the first step in checking an alternating series is basically we're just going to check using our nth term test that we've done many times before. But when we do this, we're only going to look at the positive values of each one of these terms. We're not going to worry about negative, positive. So really we're just talking about the absolute value of this thing here, or we'll just eliminate that -1 to the n. And we're just looking at n squared divided by n squared plus 1. And we know as we look at this and n goes to infinity, we're just going to get n squared divided by n squared, or 1. Since that is not equal to 0, we know that this will diverge. With the alternating series test, that first hurdle must be met, that nth term has to go to 0. Since it doesn't go to 0, we know that this diverges. Let's take a look at number 8. In number 8, we're looking at the sum from n equals 0 to infinity of -1 to the n divided by n factorial. Let's look at our nth term test for this one. That's our first hurdle. When we check the nth term, we're looking as the limit as n goes to infinity of just 1 over n factorial, which is pretty obvious that this is going to go to 0. The second part of this is we've got to make sure that our next term is always less than the previous term. So let's think about what's happening here. In this series, we know that, let me write it this way, each term, or nth term, is going to be n factorial. The next term is going to be the quantity of n plus 1 factorial. Is that less than each one? Well, that's pretty obvious because our denominator increases by 1 each time, which means, for example, if this is 9 factorial will be the value of the denominator. This one will be 9 factorial times the next term, 10. So obviously, this is always going to result in the nth term less than the previous term. So, based upon this, we're going to look at determining whether this converges absolutely or conditionally. This is telling us by the nth term test that our alternating series will converge. What we need to do is, second part of this, is decide that absolute or conditional that we talked about in the notes. So when we look at this, we're only going to look at this positive series and see how this converges or diverges. So if we're considering the positive series, we're just going to look at 1 divided by n factorial. And let's check and see if this converges or diverges. Well, there's a series of tests that we could use for this. The first one we might consider is the nth term test, but as we've shown up above, using this factorial, we already showed that this equals 0, which in and of itself is inconclusive. Sorry about the spelling here. Try this again. Inconclusive. when we're considering this positive series. So what's another one we could do? What about geometric series? Well, unfortunately, this is not geometric. Can't do that. What about a p-test? I looked at those today. Nope, that's not n to a power here. So our p-test is not something we can consider. What about a ratio test? Let's try that. So if we use a ratio test to test this positive series, we're going to look at this limit as n goes to infinity of the absolute value of, remember our ratio test is going to be this n plus 1 factorial over that previous term. This would best be written as just multiplying by the reciprocal n factorial divided by n plus 1 quantity factorial. And let's think about this. Isn't this the limit as n goes to infinity of 1 times 2 times 3 times dot 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 all the way up to n divided by 1 times 2 times 3 times dot 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 n, but then again times n plus 1. All of these are going to become 1s, and we're left with the limit as n goes to infinity of 1 over the quantity of n plus 1. So using our ratio test, this is going to equal 0, which is less than 1, which by our ratio test tells us that this will converge. What is this? This is the positive series, our positive series. Since our positive series converges, and based upon the alternating series test, that was these two things we did up above, the alternating series converge, the positive series converge. So check back in your notes and look at that. When this occurs, that means that this series here, this alternating series, that one will converge absolutely. By our alternating series test. And our alternating series test used the ratio test to prove this absolutely so. Since the positive series converges and the alternating series converges, the alternating series converges absolutely. Let's take a look at number 9. In number 9, we have another sum that is alternating. It's the sum from n equals 1 to infinity of negative 1 to the n divided by the square root of n. Alternating series test. First step is to take a look at the nth term. Let's check this out. With that, we're looking at the limit as n goes to infinity of just the positive series, which then means we're just worried about this denominator, the square root of n, which is going to equal 0. First hurdle passed. And the next thing we need to do is look at our terms to see that the next term is always less than the previous term. So let's compare the square root of n plus 1 to the square root of n. Well, no matter what n is, then the square root of n, as long as we're looking at n greater than or equal to 1, this is always going to work out that this term, the next term, is always going to be less than the previous term, which means a sub n plus 1 will always be less than the previous term for all of these n's greater than or equal to 1. So what are we saying here? We know that our alternating series test is passed. We know that the alternating series test will converge. Now we need to look at the positive series of this, 1 over the square root of n, and check and see if this will converge or diverge. As I'm looking at this, our nth term test that we just did up above, it was inconclusive because that equals 0. Geometric, again, not something that's necessary. P-test, wait a second. This one will work with the p-test because isn't this the same thing as the sum from n equals 1 to infinity of 1 over n to the 1/2 power? So by the p-test in this one, our p-value is 1/2. P is less than or equal to 1 in this case. Therefore, this positive series diverges, which means our initial alternating series of -1 to the n divided by the square root of n will converge, but it converges, it converges conditionally. Okay. Last one converged absolutely because it didn't really need to have a positive, negative, positive, negative because the positive series converged. This time, the alternating series converges, the positive series does not, which means the only way this thing 1 over the square root of n will converge is if each term alternates between positive and negative. Therefore, we say that the series converges conditionally. It's conditional on this alternating part of each term. Let's take a look at number 10. In number 10, we have the sine of x raised to the nth power divided by n factorial. Now, this one doesn't have one of these things in it. So alternating series, not in the classic sense, but think about this. As we go through each one of these n's, sine has a value that's positive, negative, positive, negative, positive, negative, as we go through each one of those x's. So what we can think about with this is the idea that we will have positives and negatives as we go through this, and raising them to this power would result in the fact that we would get an alternating set of terms in here. So we're going to just consider this as an alternating series to help us through this. So let's do the alternating series test. First step of the alternating series test is we look at the nth term. In this one, we're going to do just the absolute value of sine of x to the nth power. And again, this is the limit as n goes to infinity. We're going to look at that nth term, n factorial. Well, that's going to be 0 because think about it. The sine of x, the absolute value of that raised to the nth power, is always going to be less than or equal to 1 because the maximum value of this is going to be 1. All the other values, absolute value is going to be 1. All the other values are going to be between 0 and 1. To the nth power will always be less than 1. So this largest is going to be 1. This, of course, going to infinity, which means we have 0. Our first hurdle in the alternating series test is passed. Now, let's check and look at this. Let's take a look at the sine of x, absolute value of that, raised to the n plus 1 power divided by n plus 1 factorial, and compare that to the sine of x to the nth power divided by n factorial. Yeah. Well, as this gets larger and larger and larger, I think you can see where the numerator is just going to be some small number between 0 and 1 raised to the nth power, but this is going to get really, really huge. Think about 1 million factorial, and then the next one's going to be 1,000,001 times that. So the denominator is going to crush whatever's up there, especially when we add that next big number, or not add it, but multiply that next big number. So therefore we know that this converges. The alternating series will converge because the two parts of the alternating series test. The nth term is going to 0, and we know that the next term is always less than the previous term. So let's take a look at this again. And again, I'm just going through a process of determining which test to use. Hopefully what you've seen each time that our nth term test is not going to be capable of deciding this absolute or conditional, because when we consider this only the positive side of this, the absolute value of the sine of x to the n factorial, and this is, as we've shown up above, already equal to 0, or we wouldn't have gotten to this. Geometric, not even close. P-test, not necessary or not even applicable here. We're back to our ratio test. So let's use our ratio test to test this, which means we're doing the limit as n goes to infinity of the sine of x, absolute value, n plus 1, divided by n plus 1 factorial, times, reciprocal here, I'm working a little bit ahead knowing we've seen these enough that we don't need to show it as the initial ratio. So I'm multiplying this by the reciprocal of the denominator. So what we end up having here, I'll maybe rewrite it one more time so you can see. This would be the sine of x to the n plus 1 divided by the absolute value of sine of x to the n times n factorial divided by the quantity of n plus 1 factorial. That means we have the limit as n goes to infinity. This is just going to be the absolute value of sine of x, subtract our exponents, times, we'll end up with just 1 over n plus 1 in our denominator. And I think you can easily see that this is going to get really huge. The most this will ever be is a positive 1, which means this goes to 0. That means our positive series converges. Using the alternating series, we already showed that the alternating series converges. Since the positive series converges and the alternating series converges, then the original sum, this series, the sum from n equals 1 to infinity of the sine of x to the nth divided by n factorial will converge absolutely. And that should get you caught up with the rest of what we did in today's notes. Remember again, the alternating series has two parts to it when determining whether the alternating series converges. Nth term test equals 0, the next term is always less than the previous term, converges. Then we have to check for absolute or conditional. If the positive series diverges, the only way that series is going to converge is if we have an alternating series, so that we say that it converges conditionally. If the positive series also converges using whatever test is necessary, then we say that the alternating series converges absolutely. Enjoy the rest of the homework, and hopefully this will get you through it.